Hi everyone, I'm Mathieu Cocheteux, and today I'm excited to present our work on uncertainty-aware online extrinsic calibration using a conformal prediction approach. First, let's start by understanding the problem we address in this work. What is sensor calibration? Sensor calibration is a critical task in autonomous systems. There are essentially two types of calibration. Intrinsic calibration, which deals with correcting internal sensor biases, and extrinsic calibration, which focuses on spatial transformations between sensors to enable accurate sensor fusion. Our work focuses on extrinsic calibration. So, why does uncertainty quantification matter in this context? And what does it mean? Uncertainty quantification ensures confidence in calibration parameters, which is vital for the safety of autonomous systems. We classify uncertainty into epistemic uncertainty, which is model-related, and aleatoric uncertainty, which is data-related. In this work, we mostly focus on epistemic uncertainty, which is the most significant issue in this task. So what problem are we tackling exactly? Well, current state-of-the-art methods achieve accurate results. However, they do not still nor provide any uncertainty quantification for their outputs, which is why our goal is to offer guaranteed prediction intervals to improve real-world calibration reliability and to provide insights on the quality of the calibration parameters. Now, let's discuss the context of this work. Why does deep learning extrinsic calibration? There are traditional methods which provide accurate results. However, they are slow, often work offline, and almost always require some human intervention, and sometimes even the use of specific tools like targets. Meanwhile, deep learning methods enable calibration in milliseconds, without human intervention, and even online while the vehicle is moving. Moreover, it now often beats traditional methods even in accuracy. Here is an architecture overview of the network we use in this work. It is actually based on one of our previous works. It uses the 2D data from a camera and the 3D point cloud from the LiDAR as input. The LiDAR point cloud is projected to 2D using the initial extrinsic calibration parameters. And we then use the early fusion with the obtained depth map and the camera image to extract feeders. These feeders are then processed by the head of the network to refresh the calibration parameters, both in rotation and translation. Here is a brief overview of some popular methods from the state-of-the-art to estimate uncertainty in neural networks. We evaluated several methods balancing real-time feasibility, statistical guarantees, ease of use, and computational costs. You can notice most methods have a relatively high computational cost. This is why we chose Monte Carlo Dropout, which is real-time friendly, lightweight, and easy to implement. However, it does not come with statistical guarantees. This is why we combined it with Conformal Prediction to build reliable intervals. Building on this, we developed our uncertainty-aware framework. Let's now dive into our proposed method. Here is a simple overview of our method. First, we use the calibration network that I described earlier to infer calibration parameters. We will repeat this step multiple times to use Monte Carlo Dropout. We then pass its results to our conformal prediction framework to build intervals. Let's break this down into the two key components. First, Monte Carlo Dropout. It is a lightweight approximation of Bayesian methods. By applying dropout during inference, we introduce stochasticity. This means that by inferring n times on the same sample, we get n slightly different results. From these, we calculate the mean as the best estimate and the standard deviation as an indicator of the epistemic uncertainty of our network. Now, let's see how conformal prediction complements this approach. Conformal prediction post-processes predictions to provide statistically sound intervals. For this, it uses a non-conformity score. In our case, we use the uncertainty quantification obtained with the Monte Carlo Dropout in its computation. This ensures that we build interval of the right width for each sample, with a specified coverage probability, such as 95%, guaranteeing reliability. With this framework, we achieve promising results. Let's look at them next. Here are some key results on the Kitty dataset, using a LiDAR and an RGB camera. We can see that we achieve prediction intervals close to the target of 95% coverage, meaning that we try to get intervals in which we have at least 95% of the time the correct value into the interval. Our MPIW, meaning the average interval width, remains reasonable, demonstrating that the intervals are both accurate and practical. Something we avoided successfully here was to reach the interval confidence target, but with intervals so large that they would not give any useful information. Here, the intervals remain relatively narrow with regard to the corrective decalibrations. More results are available in the paper for different target values, and also a different dataset, DSEC, with which we were also able to test our method with even cameras instead of the usual RGB cameras, with also then a slightly different network. Here, we can see the same results under the form of graphs, valid intervals for 90, 95, and 99% confidence levels. And you can notice various trends here, which are actually quite natural. First, interval width is higher on the extreme left and right of each graph, meaning that when the original decalibration is higher, the chance of error is higher, which was obviously an expected behavior. Some axes also have larger intervals, especially the pitch axis. This can be explained by the fact that the Kitty dataset relies on the LiDAR model, which has a much lower vertical resolution compared to its horizontal resolution, meaning that the risk of error is much higher when matching the data, especially on the pitch axis. This is what translates into these larger intervals. To conclude, we introduced a novel framework for uncertainty-aware online calibration using conformal prediction. This approach improves sensor fusion reliability with statistically guaranteed prediction intervals, and we demonstrated high accuracy and robust intervals on Kitty and DSEC datasets. Future efforts will focus on optimizing the framework for large-scale deployments and extending it to other sensor combinations. Thanks for watching, and feel free to reach out via email or find more details on arXiv.